Hello there, and welcome to this video about the periodic table for GCSE chemistry. This is the first video of 6 short videos, each exploring different aspects of the periodic table. In this video, we're going to be looking at how we can explore and navigate the periodic table. We'll take a look at the different ways that we can use the periodic table as a tool, including what we can learn about subatomic particles from the information in the periodic table. And we'll also take a look at how we can predict properties of the different elements in a particular group in the periodic table. The periodic table contains all the known elements, which is about 100 of them. Now the table is organised in order of increasing atomic number, which is this lower number here, and you can see that hydrogen has got an atomic number of 1. What we mean by increasing atomic number is as you read left to right as if you were reading a book, hydrogen is 1, helium is 2, and then we've come to the end of this row, so we move down to the next, and lithium is 3, beryllium is 4, boron 5, etc., carrying on and increasing by 1 each time you move one step left in the periodic table. Another thing you'll notice about the periodic table is that all of the elements have got their own unique symbol. Each symbol has got one capital letter, so hydrogen is a capital H. Helium, which also begins with an H, has got a capital H, but it's got an E as well, and that allows you to tell the difference between helium and hydrogen when we're using symbols. There are other elements as well that have got a symbol that begins with an H. There is mercury, Hg, little g, so a lowercase g for the second letter. Now we can navigate our way around the periodic table by talking about things called groups. Groups are the columns in the periodic table, and the columns are the things that go up and down. And so this here is called group 1, which is also called the alkali metals. Group 2 is the next one along. Then we have a gap in the middle, and this gap is called the transition elements, sometimes called the transition metals. And then we get to group 3, group 4, group 5, group 6, group 7, and then this is most commonly called group 0, but it is also sometimes called group 8. And so those are the different groups. Then along this side, I'm going to write the period number. And these periods are the rows, and they go side to side. And so I could say I'm thinking of an element, it is in period 3, group 5. So we'd find our way down, period 1, 2, 3, move along to group 5, and I was thinking about phosphorus. We must remember to account for period 1. It's really easy to overlook it because hydrogen is often shown over here, because it has some things in common with the other elements in its group, but not everything. And so it's very easy to overlook. And sometimes I encourage people to write the period numbers down the right-hand side as well, because that way you can see that period 1 is definitely this first very short row that includes helium and hydrogen. The last thing I want to add on this first periodic table is the metals and the non-metals. Now, of the 100 or so elements that there are in the periodic table, the vast majority of them are metals. In fact, the dividing line is here between metals and non-metals, and it sort of looks a bit like a set of stairs, like this. And these stairs divide the metals, which are everything to the left of it, from the non-metals, which is this much smaller group on the right-hand side. And it also includes hydrogen. This sort of set of stairs kind of continues over to include hydrogen as well, because hydrogen is a non-metal. Let's take a little bit of a look now at how we can use the periodic table to learn more about the elements. You will have studied this in the atomic structure topic, and you might have watched my atomic structure video, but this is a quick recap. As I've already said, every element has got an atomic number. Now it's sometimes written as the atomic, or in brackets, proton number. And unsurprisingly, that tells you how many protons there are in the nucleus of each element. Now remember that protons are positive and the electrons have got a negative charge, and overall atoms have got no charge. And so what that means is that the number of protons and the number of electrons are always the same. So we can pick any element we like. I'm going to pick boron. Boron has got an atomic number of 5, and that 5 means that boron has got 5 protons, and it will also have 5 electrons as well. If I pick fluorine with an atomic number of 9, fluorine will have 9 protons, and it will also have 9 electrons too. Moving down here to mercury, mercury has got 80 protons, and it's also got 80 electrons. I'll just do one last one down here for cesium. Cesium has got 55 protons, and it's got 55 electrons as well. Now every element also has a second number, and that is the mass number. Now the mass number is the number of things in the nucleus, which are sometimes called nucleons. So the nucleons are the things in the nucleus, and that is the protons and neutrons. And so what that means is, if an element has got, let's pick lithium, an atomic number of 3, it's got 3 protons. It's got a mass number of 7, that means the number of protons and the number of neutrons adds together to make 7. So if it's got 3 protons, and we need to add the number of neutrons to that 3 to get 7, the neutrons must be 4. Or, to put it a different way that's much more usable, the number of neutrons can be found by taking the mass number and subtracting the atomic number from it. And so, if we start looking at the examples we looked at before, boron with a mass number of 11, 11 take away 5 equals 6. That means that boron has got 6 neutrons. If we move on to look at fluorine, which has got a mass number of 19, 19 take away the atomic number 9 equals 10 neutrons. And moving down to mercury, 201 is its mass number. 201 take away 80 is 121 neutrons. And last of all, cesium, 133 is the mass number. 133 take away 55 is 78 neutrons. And so the periodic table can be used to find out about these subatomic particles, the protons and neutrons that are in the nucleus, and the electrons which are found in shells, remember. I want to keep thinking about electrons now by looking at the electron arrangement for each of the elements. The electron arrangement is sometimes also called the electronic structure, but it means the same thing. And what we mean by that is how many electrons there are in each shell for each particular element. Now, I'm hoping that you'll remember that the first shell can hold 2 electrons as a maximum, and the second shell has a maximum, and it's 8, and the third shell is also 8 as a maximum. And then the fourth shell, well, we don't need to know about that. The maximum that you're going to be expected to put into it is, in fact, 2, because you're only going to be asked about the first 20 elements, which is up to here in the periodic table. Now, I want to show you how we can work it out, but I also want to show you how we can predict without feeling like we have to work it out. So let's start here with boron. This was boron in this box on here. Now, we found out that boron had got 5 electrons, And so we have to put 2 electrons into the first shell, and then that shell is full, and then we put 3 into the next shell, and then we've run out of electrons. So that's the end of boron. Now this next one over here, this was fluorine, and fluorine had 9 electrons if you remember. We put 2 into the first shell, and we put 7 into the next, and then that one is full. Now we're not going to do mercury because that's too many electrons, but let's move down here to sodium. And sodium, we didn't do it, so I'll put the atomic number there. It's 11. And so what happens for sodium is we put 2 into the first shell, and then it's full. 8 goes into the next shell, and then that's full. And the last one goes into the third shell, and then we've used that up. What I'm going to do now is I'm going to fill in the rest of these. You can just make a few predictions yourself just to check that you are understanding this, but then I'm going to put them all in at once now. Okay, I've filled in the rest of the first 20 elements in terms of how many electrons each shell has got in it. And I'm hoping now that we'll start to see some patterns. If we take a look at group 1 in the periodic table, we should, I hope, notice that the final shell of electrons for each element in group 1 only contains 1 electron in it. And that is why we place these 4 elements, hydrogen, lithium, sodium and potassium, into group 1 in the periodic table. And then the elements in group 2, each of their electronic structures ends in 2, meaning that they've got 2 electrons in their outer shell. Moving on to group 3, over here, they end in a 3, meaning that they have 3 electrons in their outer shell. Group 4 have got 4, group 5, group 6 and group 7 follow the pattern that you would expect. You can see why this group is often called group 8, because these 2 elements, their electron structures end in 8. But this top one doesn't, it only ends in 2, and that's because the first shell can only hold 2. So these group 8 elements have got full outer shells, but because the first element, helium, doesn't have 8 electrons in it, it only has 2, we sometimes call it group 0, with that 0 representing, amongst other things, that full shell of electrons. And so the group number for any element tells you the number of electrons it has got in its outer shell, sometimes called valence electrons. Now the other clever thing, if I just rub out sodium's symbol over here, is if we take a look at the period number, remembering period 1, 2, 3, 4, etc., we can see that the elements in period 1 have got 1 occupied shell of electrons because there is only 1 number. The elements in period 2 have got 1, 2 occupied shells. 1, 2 occupied shells. And that's the same with period 3, 1, 2, 3 occupied shells. Period 4, 1, 2, 3, 4 occupied shells. So the period number tells us the number of occupied electron shells. So we might not know what element we're talking about, but if we're talking about something in period 2, we know it's got 2 occupied shells of electrons. And then if I say it's in period 3, we know that there are 3 electrons in that outermost occupied shell. Now the reason I've been talking about electrons for so long is because they're really important to help us understand the arrangement of the periodic table. Now, the title for this slide is called Periodicity, and that is the study of repeating patterns. And the clever thing about the periodic table is that similar patterns occur at regular intervals. And the fact that these patterns occur at regular intervals is what makes the periodic table so powerful, and it's what led to so much time being needed to come up with the design for the periodic table of elements. So what we mean by the periodic pattern, the pattern occurring at regular intervals, is that if you take an element, and I'm going to pick lithium, and we count 8 elements on 1, 2, 3, 4, 5, 6, 7, 8, we arrive back at an element that is really, really similar to lithium. And if we count on another 8, 1, 2, 3, 4, 5, 6, 7, 8, we arrive at potassium, which is another similar element to lithium. And we learnt on the previous page that all the elements of group 1, the alkali metals, behave in a similar way. And that's to do with the electrons that they've got in their outer shell, the valence shell. And they all have one electron in their outer shell. And so we can predict, if we look at the reactivity of these three, which you'd probably study in school, but then we don't know about rubidium or cesium or francium, we can make predictions that they will behave in a very similar way chemically when you, for instance, put them into water. And in the same way, if we look at group 7, which is called the halogens, and we know that fluorine and chlorine and bromine behave in certain ways, and say iodine as well, you're likely to study all 4 of those in class, but we don't know about astatine and tennessine. We don't know so much about those, but we can make predictions that they will all behave in a similar way, and we can also make predictions about the patterns of which of them are likely to be more reactive. Will it be fluorine or will it be tennessine? Will it be francium or will it be lithium? We can use our knowledge of the periodic table and electron shells to help us understand that. And last of all, the final group that I'm going to look at right now, which is the noble gases. Now the noble gases, because they've got a complete outer shell, a full valence shell of electrons, that's what makes them unreactive. So we can make the prediction that these elements are all going to be unreactive, and that's all down to the electronic structure that they share in common. So we can use the electronic structure to make predictions about similarities between different elements in the same group, but also to make predictions about which element will be the most reactive in any particular group. To finish off this video, I want to spend a bit of time considering the differences between metals and non-metals. Now, we've already looked at where we find them in the periodic table, but I want to say a little bit more than that. Now, firstly, metals, what they have in common is that when they react with other elements, they form positively charged ions. And they do that by giving away their electrons. Non-metals, in contrast, they form negatively charged ions. And they do that by gaining negatively charged electrons. Alternatively, another thing that separates non-metals from metals is that non-metals can share electrons. And when they do that, they make something called a covalent bond. Now, both of those can't happen at the same time. You'll either get a metal, which will give one of its electrons away to a non-metal, and that will leave the metal being positively charged and the non-metal being negatively charged, having gained an electron. Or alternatively, you will get 2 non-metals that will share a pair of electrons in a covalent bond. So this is called ionic, that you will have learnt about in another topic, and this is called covalent. I'm going to put covalent bonding on one side for the rest of this video, and I just want to take a little bit more of a look at the charge of different ions. A really powerful tool in the periodic table is for us to learn what charge something will have when it becomes an ion. Now, to do that, we need to remind ourselves about what it means to be in certain groups in the periodic table. So if I just move my periodic table to the side here, and we think about the groups that elements are in. Now we know that this is group 1, this is group 2, 3, 4, 5, 6, 7 and 0. Now the outer shell electrons, or the valence electrons, we know that that means group 1 have got 1 electron in their outer shell, 2 have got 2, then 3, 4, 5, 6, 7 and then 2 or 8. Now here's the next bit. To get a full shell, and the significance of this is when something gets a full outer shell of electrons, it becomes stable. So that is the main purpose of forming a bond between one element and another. It is to achieve a full outer shell of electrons. So lithium and all the other elements in group 1 have got 1 electron in their outer shell. So they could either gain 7 more to fill the shell or lose 1 electron. And it is far easier for lithium to lose 1 electron. And in the same way, all the elements in group 2 need to lose 2 electrons. Group 3 need to lose 3 electrons. Group 4, now group 4 is weird because gaining 4 electrons and losing 4 electrons, both of those are really difficult to do. So generally they don't form ions, they bond covalently. Nitrogen and all the elements in group 5, well, they have got 5 electrons in their outer shell already. They need a total of 8, so they gain 3 electrons. Oxygen and all the elements in group 6, they need to gain 2 electrons because 6 and 2 makes 8. And last of all, fluorine needs to gain 1 electron to get a full shell. The noble gases in group 0, they don't need to gain or lose any electrons to get a full shell because they already have 1. Last of all then, what's the significance of this losing and gaining electrons? Well, if I have lost 1 electron, I will form a 1+ ion, and all the elements in group 1 form 1+ ions. And group 2 always form 2+ ions. Group 3 form 3+. Group 4 don't generally form ions. Group 5 would be 3-, then 2-, then 1-, and then noble gases don't form ions. So you can make predictions about the electronic structure and about the charge of positive metal ions or negative non-metal ions just by looking at the periodic table and the position an element has in a particular group. And if you can master that skill, it will make bonding and other topics so much easier as well. Finally, I just want to take a quick look at some metal and non-metal properties. Now, before I do that, I need to define what a property is. So a property is a characteristic. It's a describing word that gives you some information about what a substance is like. So, for instance, metals are strong, which means that they are very hard to break, but they can be hammered or bent into different shapes, which is what the word malleable means. Metals are also very good conductors of heat, which means they let the heat energy pass through them, and they're good conductors of electricity as well. In general, they tend to have high melting point and a high boiling point, and melting point is the temperature at which a solid turns into a liquid, and the boiling point is the temperature that a liquid turns into a gas. As a consequence of those two properties, generally metals are solid at room temperature, with the exception of mercury, which is one of only 2 elements in the periodic table to be a liquid, the other one being bromine, at room temperature that is. And last of all, in general, metals also have a high density, which means if you have, say, a handful of a metal and a handful of a non-metal, the metal is likely to feel much heavier in your hand because it's got a higher density. In contrast to metals, non-metals are generally dull, where metals can be really polished to a high shine. They're also quite brittle instead of being strong. They generally have much lower melting points and boiling points, that's my abbreviation for those, which means that often they aren't solids at room temperature. Quite commonly they are gases, but there are some solids, and that one liquid that I mentioned, bromine, as well. They often have a much lower density than metals, and in general they don't conduct electricity, although there is one exception, which is graphite. Now, to finish off, what I should say is that all of these properties that I've listed here are what's known as physical properties. Now, physical properties, they can be sort of observed or measured without changing the element that you're observing, as opposed to things like chemical properties, which is how substances behave when you react them with oxygen or acids or water or something like that. So all of these properties that we've been looking at here are physical, observable properties, as opposed to things that you have to discover through doing chemical reactions. We'll look at some of those in other videos coming up in the next few days when we start looking at alkali metals and the halogens. Okay, that's all for this introductory video. I hope it was useful. We'll have a look at the history of the periodic table in this second video about GCSE periodic table. Okay, bye-bye. See you next time.